All right, welcome to Unit 1, Exploring One Variable Data. Today's topic is going to be over graphical representations of summary statistics. So in the previous video, we learned about all the different summary statistics for a set of data, a set of quantitative data. We talked about mean and median for center. We talked about standard deviation, IQR, and range for spread. And now we're going to talk about how we could use that representation of summary statistics to make a nice graph. All right. So first off, let's talk about what the 5-number summary is. The 5-number summary of a set of data taken together is the minimum data value, the first quartile, the median, the third quartile, and the max. This makes up the 5-number summary, so just keep that in mind. Min, first quartile, median, third quartile, and maximum. Basically what the 5-number summary does is it splits your data into force, right? So if you think about your data like this, here's the min, over here's the max, right? Somewhere in the middle, the exact center of all your data is going to be the median. And then the middle of the bottom half is Q1, and then the middle of the top half is Q3. So by using the 5-number summary, you're splitting your data up into force. So you got the bottom 25%, you got the top 25%, and then you have the overall middle 50%, right? That's the IQR between Q3 and Q1, and that gets split up as well. So it's really kind of splits your data up very nicely into these 25% chunks. That's what the 5-number summary does. So understanding what each of these values represents allows the 5-number summary to be a nice way to describe and understand the variation within a set of data. All right, with the 5-number summary, you can make what's called a box plot. I really hope every single one of you has heard of a box plot before. So a box plot is a graphical representation of the 5-number summary. The box itself represents the middle 50% of the data from Q1 to Q3. So you make a box around Q1 and Q3. And then somewhere in between those two values is the median. You're going to put a line there at the median. Now, it does not have to be dead center, right? A lot of kids think that the median is exactly between Q1 and Q3. No. Not necessarily, right? It's somewhere in between, but you got to think about how your data varies. And again, that's what a box plot allows us to see. So we'll talk about that. Then you make lines, which most people call whiskers, that extend from the quartiles out to the most extreme points that are not outliers. So maybe back in younger grades, you learned that the whisker goes to the max, the bottom whisker goes to the min. No. If you have outliers, the whiskers or the lines go to the highest values or the lowest values that are not outliers. So you do have to check and see if you have outliers first. And if you do have outliers, you usually indicate them with their own symbol, like a little asterisk or a dot. So here's a picture of what a box plot ends up looking like. First and foremost, you absolutely need a number line underneath. You need a number line underneath so you know where the heck to put the values, right? So we make a box around the first quartile right here and the third quartile to make a box around that. And then the median as a line within that box, okay? Then if you do have outliers, they get their own separate symbol. For example, I must have checked the data here and we use the outliers. Remember the outlier formula to find any lower outliers is Q1 minus 1.5 times the IQR. So once you determine that you do have values below that fence, and by the way, that fence does not get graphically represented on the box plot at all. The lower fence is just a number that you use to help understand if you have outliers. So once you said, okay, these 3 guys here are outliers, you make little dots at these 3 values, and then you have to look at your data, and the whisker goes to the next value that was not an outlier. So that means this value right here was, again, the lowest value that was not deemed an outlier. And then if you have, if you check your upper fence by using Q3 plus 1.5 times the IQR, and you realize, wow, I don't have any upper outliers, then your whisker will go to the max because you didn't have any outliers. So this is a nice way to break up your data. And it's really important to understand what you're doing when you make a box plot is you're breaking your data down into quarters. So below Q1, Q1's right here, below Q1 is 25% of your data. In between Q1 and the median is 25% of your data. Median to Q3 is 25% of your data. And anywhere above Q3 is also 25% of your data. Now, a lot of kids think, oh, if there's a bigger part, if this box over here, from here to here, it's bigger, that means there's more data. No. Every one of these chunks contains the exact same amount of data, 25%. When you have a wider box or a wider whisker, all that means is that the data in that location is more spread out. So the width of the whiskers, the width of the box represents how spread out the data is. We specifically break the data down into these 25% chunks so that every single portion of a box plot contains the exact same amount of data, but it allows you to see how variability there is within that area by how wide it is. All right, so what can we learn from data? The summary statistics and graphs of quantitative data can be used to justify claims about the data in context. The whole reason why we have summary statistics, the whole reason why we have the outlier formulas, the whole reason why we make graphs, whether it be a histogram or a dot plot or now a box plot, is because we want to be able to say something about that data. And if we're going to say something about data, we better have a solid reason to back it up. Like if you're going to say data skewed right, I better see that in the graph, right? If you're going to say, oh, the mean is this, well, I want to know that from the data, right? So using everything we've kind of learned so far is just a way to basically back up claims that we're going to make about data. And the cool thing about box plots is you can see shape, center, and variability all in a box plot, just like you can in a histogram or dot plot or stem and leaf plot. All right, let's talk a little bit about center. If you are symmetric, if a distribution is relatively symmetric, the mean and median are going to be very close to each other. So if you find your mean and median and they are really close to each other, right? They don't have to be exactly the same, but fairly close. That is a guaranteed sign that your data is fairly symmetric, all right? If your distribution is skewed to the right, then the mean is always going to be a little bit higher than the median. That's a sign of skewed right. Because remember, if your data looks like this, skewed right, yeah, there's a ton of data in this bottom quarter, right? In this bottom quarter right here, there's a ton of data, a lot more than the upper quarter. But the mean has to take everybody into account, so these few higher values are going to impact the mean. You could think about it like this, like one really big high upper value in and of itself is equal to maybe a whole bunch of lower values. And that is why one value at the top is enough to influence the mean to move up a little bit, where the median doesn't care, right? The median just wants to be in the dead center. The median doesn't care at all what the values are. So when you're skewed right, the mean's going to go a little bit towards that tail and be bigger than the median. When you're skewed left, the opposite happens, right? We have a couple lower values, and then we have a lot more higher values. So again, the mean has to take these lower values into account. Even though there's not a whole bunch of them, the mean has to be fair and treat everybody equally, so the mean is going to go a little bit lower. Well, once again, the median doesn't care. The median just wants to be in the dead center of all your data. So what happens here is that when you're skewed left, the mean is going to go towards the left a little bit lower than the median. So it's a nice way to kind of understand your data just by looking at the mean and median. If they're pretty much the same, symmetric, if the mean is bigger, you're going to be skewed right. If the mean is lower, you're going to be skewed left. Now, why? Why is this? When data is symmetric and balanced, the mean gets equally impacted by both the numbers on the right and the numbers on the left. So since it's balanced, it ends up being right in the middle, exactly where the median always is. That's why they're really close to the same when you're symmetric. When data is unbalanced, say skewed to the right, the larger values to the right impact the mean more, and the mean moves to the right. Even though there are not many of these high values to the right, they weigh more and they tip the scales. But the median is always in the middle no matter what. So the mean ends up being a little bit higher than the median. That's why when you're skewed right, the mean moves to the right. It's a little bit higher. All right, now the cool thing about box plots is you could see symmetric and skewed in box plots as well. So here's 3 examples of box plots. Now none of them have outliers, but you could almost see, right? For example, on this top one, this represents 25% of data, and so does this. Just because the lower list is longer doesn't mean more data. It just means that data is more spread out. So up here, the data might be spread like this, and then down here, the data is much more spread out. Same amount of data. Now, I didn't actually count my dots to make sure of that, but just trust me, right? That on the left, it's just more spread out. Same within the box, right? This 25% of data and this 25% of data, they're both the same amount of data, right? There's not more data in this bottom box. It's just more spread out. So if you think about it, there's 50% of data up here, right? And there is 50% of data down here. but the bottom 50% is more spread out, so that's going to lead to a graph that is skewed to the left, right? So there's a lot of data down here, but on the far right, we have more data clustered together, which makes that skewed left. Here's a nice example of symmetric. And we see that the bottom 25% is pretty equal to the top 25% in terms of spread. Same thing with the middle 25 and the upper 25. They're pretty much spread out the same. Not exactly, but pretty close. That's going to be a sign of nice and symmetric and unimodal data. And then we have right skewed. Right skewed here is, again, we have our bottom 50%, right, below the median, and then we have our upper 50% above the median, and you can clearly see that the upper 50% is more spread out. Again, same amount of data on both sides of the median, but on the right, it's more spread out, which is going to cause that skewed right graph. So it's kind of nice that you could see that in these graphs, right? It's a nice way to see shape. So when we talk about shape, you can easily see it in these graphs. All right. Here's another example, right? This is, I actually put a number line here because this is, again, you got to have that number line. So these are quiz scores, right? So, 25% of kids score between a 30 and looks like maybe the median is, again, you kind of have to estimate this, maybe 63. So between 30 and 63, 25% of kids scored that. Well, guess what? 25% of kids also score between a 63 and a 70 right here. But on the left side, it's much more spread out. So let's just say that there were 10 kids here. They were spread out all throughout here. Try to get 10 dots here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They were nice and spread out away from 30 to 63. Whereas the 10 kids in here, they were very clustered together, all hovering in that 63 to 70 range. And then same thing with the whiskers. 25% here, 25% here. So the upper 25% is definitely spread out more than the bottom 25%. These kids, the 25% of kids were all stuck between 20 and 30, right? Now, I kind of told you 10, right? If there's 10, that means there's going to be 10 kids in every section. And that means there's 40 total kids, 25%, 25%, 25, 25. Now, if I don't tell you sample size, you cannot make any claims about how many kids fall into these regions. You would have to use proportions, right? So it kind of goes back to that idea that if you don't know your sample size, you're kind of relying on proportions to understand the data because you don't actually see the data in a box plot. All right? So it's pretty easy, right? It's just a nice way of looking at your data and understanding where the data falls, where the data varies more, where the data varies less. All right, here's one more box plot. This is a side-by-side box plot, and we see one that's going vertically. Vertically, horizontally, doesn't really matter. You'll see kind of both here. So what we did was we looked at a bunch of adults from North Carolina, a bunch of adults from New York, and we simply asked them how long does it take to get to work, their commute time. And we made these box plots here. And it's a nice way to compare, right? For example, we see that New York does have an outlier. All the way up here, it takes somebody about 82-ish minutes to get to work, right? So that's an outlier. And then we see that the median for New York is slightly higher than the median for North Carolina. Looks like the median for North Carolina is somewhere around 20. For New York, it might be somewhere around 22 minutes. We see a nice spread here, right? For New York, the upper 50% above the median is much more spread out. Same thing, the North Carolina is not symmetric, but the middle 50% is kind of symmetric. It's that top whisker that's a little bit more spread out. The IQR, that's between Q1 and Q3, is much smaller for North Carolina than New York. And you don't even have to measure it. You can literally just see it in the data. You can just see that the boxes are wider. That's going to be more spread out. So New York has definitely a bigger spread. Again, I don't really like calculating range too much, to be quite honest, but the range for New York is much bigger because of that outlier. Remember, when you're talking about range, outliers matter, right? You're going max to min. So there's a huge range of data for New York, whereas North Carolina with no outliers has a little bit of a smaller range there. So it's a really nice way to kind of compare the data. And again, you could see the center. You could see the shape, like we talked about, skewed right. I'd say both of these are a little bit skewed right. And we could also have a good idea of variability, right? We could talk about who has the bigger spread in the middle 50%. So New York has a bigger IQR, so it's more spread out in the middle. So there's a lot of cool stuff that you could see and understand when you're looking at a box plot. All right? So just remember, key thing I need you to understand is a box plot separates your data into quarters. So it uses the 5-number summary to separate your data into quarters. Pretty nice and simple.